Remember when smoldering MS was just a theory? Well, now it does seem like it's more than that because research has started to understand exactly why smoldering MS exists and how it works. Well, hello and welcome to another episode of You and Me and Multiple Sclerosis. My name is Pam. I've been living with MS for almost 40 years. And over those decades, it did seem like we went through a long stretch where all that was really going on was new DMTs coming out that were sort of variations on a theme, always looking to control the number of relapses, usually with something to do with T cells or B cells. Not that I'm implying that T cells and B cells aren't important, because of course they are. But what became obvious to doctors over time was that people with MS continued to get worse even when their MRIs didn't show any more damage going on, at least not visibly. And that got them thinking there must be something else at play here besides just controlling relapses. And out of that came the theory of smoldering MS. And you might remember I made a video some time back. Professor G had posted a Substack podcast where he was pretty discouraged because the smoldering MS idea just didn't really seem to be taking hold. But I was sure that it would sooner or later because it made so much sense. And guess what? It does look indeed as if that has happened. I just want to show you here an ad for a pharmaceutical company you may have heard of, Sanofi, talking about this exact thing.
Emerging science has revealed that not one but two largely independent but concurrent neuroinflammatory pathways drive disease progression from the onset of MS. The focus to date has been on addressing relapses and lesions caused by acute neuroinflammation, which is driven largely by activated B cells and T cells derived from the periphery that migrate into the CNS. However, despite effective control of their relapse and acute lesion activity, many patients continue to accumulate significant physical and cognitive disability, thought to be driven by smoldering neuroinflammation. Smoldering neuroinflammation occurs early in the disease process and is driven primarily by pathogenic microglia. Bruton's tyrosine kinase, or BTK, plays a critical role in their activation, as well as the activation of B cells. Pathogenic microglia are associated with an increased release of pro-inflammatory cytokines, ongoing axonal injury, development of chronic active lesions, and neurodegeneration, resulting in disability accumulation. Smoldering neuroinflammation occurs only in the CNS behind an intact, highly selective blood-brain barrier. It has not been directly addressed because of the inability to cross the blood-brain barrier and act at pharmacologically relevant levels. Targeting the immune cells driving both acute and smoldering neuroinflammation may improve long-term outcomes, bringing hope to patients with MS.
So see, smoldering MS has made the big time, and they're starting to understand the reasons for it having to do with microglia. Not that I'm implying that T cells and B cells aren't important, because of course they are. And here's an article from MSology that gets at just that exact thing. It says it much better than I could say it, so I'm going to go ahead and read just this one part of it for you. This article was in MSology on their website back in May 6th of 2024. It may be not entirely up to date because a lot has happened since then, but I think that the basic idea provides some context for what I'm going to show you today. And the article is called 3 Reasons for Hope During MS Awareness Month. I'm only going to look at one of those, and let's go ahead and take a look at that. Number 1, rethinking the disease process. Relapses are the most obvious feature of MS and have been the main focus of attention for decades. The thinking was that relapses caused an accumulation of nerve damage in people with MS that ultimately led to disability. So treatments were developed to reduce the frequency and severity of relapses. That narrow focus on relapses underwent a sea change a few years ago, when researchers recognized that disability, or in other words, disease progression, got worse even when there were no relapses. And they've got a reference there that you can look up. This phenomenon would become known as PIRA, for progression independent of relapse activity. 2 years later, a study found that about 90% of progression events when disability got worse and never improved were in fact PIRA. And there's another reference for you to look at. For all intents and purposes, PIRA is neurological disability, which has had enormous implications for MS research and treatment. And there's another reference for you to look at. First, while relapse reduction certainly makes life better for people living with MS, it does not appear to be a very good measure of whether a treatment is working or not. Relapses are not the target. The true target is neurodegeneration that results in disability. This has spurred researchers to look at the very complex mechanisms at work in the brain that contribute to disability, as well as the healing mechanisms that could repair nerve damage. Finding the right target or targets is challenging, but work is now underway to explore dozens of novel medications. And you and I have looked at a lot of those over the last few months. Secondly, there is a need to change how treatment success is evaluated. The old measure of success, reducing relapses, will no longer serve. This was seen in the recent trial of ibrutinib, a novel brain-active drug that used relapse reduction as an indicator of treatment success, rather than a measure demonstrating an impact on neurodegeneration. The trial failed on this score, and ibrutinib is no longer being developed. It remains to be seen if other drugs in this class are able to show that new efficacy measures translate to long-term benefits. And there's another reference for you to look at. And now that we've looked at this article, I think it might make more sense if we go ahead and look at what I want to talk about today, which is not going to mention MS specifically. But you'll see, I think, as we get into it, how what the research is looking at relates to multiple sclerosis in a new and kind of exciting way. I saw this article on the BBC website. It's called "The Cells That Protect Your Brain Against Infection Could Also Be Behind Some Chronic Diseases." This was published in October of 2024, and the author goes on to say microglia are the brain's resident immune cells. Their job is to patrol the brain's blood vessels looking for invading pathogens to gobble up. But what happens when they go rogue? Historically, they've been overlooked, seen as simple foot soldiers of the immune system. Yet increasingly, scientists believe that microglia may have a more directional role, controlling phenomenon from addiction to pain. Some believe they may even play a key role in conditions such as Alzheimer's disease, depression, anxiety, long COVID, and myalgic encephalomyelitis, also known as chronic fatigue syndrome. They don't list it here, but multiple sclerosis would fall into this category as well. I'm sure of that. And based on some of the videos that I've shown you in the past, this seems very relevant. So, as I said, even though they're not going to mention multiple sclerosis here in this article, I think that what they have to say is very relevant to us. But what exactly are microglia, they ask? There are two types of cells that make up the brain. Neurons, also known as nerve cells, are the brain's messengers, sending information all over the body via electrical impulses. The other type, glia, make up the rest. Microglia are the smallest member of the glia family and account for about 10% of all brain cells. The smallest cells have a central oval-shaped body from which slender tendril-like arms emerge. They have a lot of branches that they are continually moving around to survey their environment, says Paolo Derrico, a neuroscientist at the University of Freiburg, Germany. In normal conditions, they extend and retract these processes in order to sense what is happening around them. I'm going to insert this short clip that I found. It shows the microglia. It's kind of almost creepy in a way, watching them swim around and gobble up things. But that's going on in our bodies all the time, and it's essential for our immune system to work properly. But you can also see how it could get out of control. When performing well, microglia are essential to healthy brain function. During our early years, they control how our brain develops by pruning unnecessary synaptic connections between neurons. They influence which cells turn into neurons and repair and maintain myelin, a protective layer of insulation encasing neurons, without which transmission of electrical impulses would be impossible. Their role doesn't stop there. Throughout our lifetimes, microglia protect our brains from infection by seeking out and destroying bacteria and viruses. They clean up debris that accumulates between nerve cells and root out and destroy toxic, misshapen proteins such as amyloid plaques, the clumps of proteins thought to play a role in the progression of Alzheimer's disease. Yet in certain circumstances, they can go rogue. There's two sides to microglia, a good side and a bad side, says Linda Watkins, a neurologist at the University of Colorado Boulder. They survey for problems looking for unusual neural activity and damage. They're on the watch for any kind of problems within the brain, but when they get super excited, they turn from being the vigilant good guys to the pathological bad ones. When I read this, it caught my attention because I've said to you multiple times that I look at multiple sclerosis as sort of a disease of overreaction, and it sounds like it's happening at the microglial level, that hyperactivity is actually at the cellular level. We are the summation of our cells, of course, to a certain extent, at least physically we are, and it is difficult to ignore the fact that if these microglia are getting hyperexcited, it wouldn't manifest in some way in our own behavior. As they say here in the poll quote, out of control microglia are now thought to be behind a variety of modern diseases and conditions. And again, they don't list MS, but I think MS belongs in this category. What makes them go rogue? When microglia sense that there is something wrong in the brain, such as an infection, or a large presence of amyloid plaques, they switch into a super-reactive state. They become much larger, almost like big balloons, and they pull in their appendages and start moving around, munching up damage like little Pac-Mans, says Watkins. I like that picture. An activated microglia also release substances known as inflammatory cytokines, which serve as a beacon calling other immune cells and microglia to action. Such a response is necessary to help the body fight off invaders and threats. Usually after a certain amount of time, microglia revert back to their quote-unquote good status. However, it appears sometimes microglia can stay in this superexcited state long after the infectious agent has disappeared. These out-of-control microglia are now thought to be behind a variety of modern diseases and conditions. Take addiction. This condition has historically been viewed as a disorder of the dopamine neurotransmitter system, with imbalances of dopamine being to blame for sufferers' increasingly drug-focused behavior. But Watkins has a different theory. In a recent academic article, Watkins and scientists from the Chinese Academy of Science argue that when a person takes a drug, their microglia see the substance as a foreign invader. What we found out through our own research was that a variety of opiates activate microglial cells, and they do so at least in part through what's called the toll-like receptor, or TLR, says Watkins. Toll-like receptors are very ancient receptors designed to recognize foreign objects. They're supposed to be there to detect fungi, bacteria, and viruses. They're the not me, not right, not okay receptors. And where would we be without them, I have to say. When microglia detect drugs such as opiates, cocaine, or methamphetamine, They release cytokines, which causes the neurons that are active at the time of drug taking to become more excitable. Crucially, this leads to new and stronger connections between the neurons being formed, and more dopamine being released, strengthening the desire and craving for drugs. The microglia change the very architecture of the brain's neurons, leading to drug-taking habits that can last a lifetime. So this is kind of like a neuroplasticity thing, right? In a bad way. The evidence to support this theory is compelling. For one, drug abusers have raised inflammation and inflammatory cytokines in the brain. Reducing inflammation in animals also reduces drug-seeking behavior. Watkins' team also has shown that you can stop mice from continually seeking out drugs like cocaine by blocking the TLR receptor and preventing microglial activation. Once again, those mice, I'm telling you, where would we be without them? And as this quote says, with aging, glial cells become more and more primed and ready to over-respond as the years go by. Linda Watkins again. Microglia could play an important role in chronic pain too, defined as pain that lasts longer than 12 weeks. Watkins' laboratory has shown that after an injury, microglia in the spinal cord become activated, releasing inflammatory cytokines that sensitize pain neurons. So now we're talking about the connection between the microglia and pain. If you block the activation of the microglia or their pro-inflammatory products, then you block the pain, says Watkins. According to Watkins, microglia could even explain another phenomenon: why elderly people experience a sharp decline in their cognitive abilities following a surgery or infection. The surgery or infection serves as a first hit which primes microglia, making them more likely to adopt their bad guy status. Following surgery, patients are often given opioids as pain relief, which unfortunately activates microglia again, causing an inflammation storm that eventually causes the destruction of neurons. The field of research is in its infancy, so these early findings should be treated cautiously. But studies have shown that you can prevent post-surgery memory decline in mice by blocking their microglia. If I walk up to you and without any forewarning whatsoever slap you across the face, I get away with it the first time. But you don't let me get away with it the second time because you're primed, you're ready, you're on guard, says Watkins. Glial cells are the same way. With aging, glial cells become more and more primed and ready to over-respond as the years go by. And so now that they're in this prime state, a second challenge like surgery makes them explode into action so much stronger than before. Then you get opioids, which are a third hit. Now I'm curious, does this ring any bells for any of you? And I don't think it really makes a difference if you're elderly. If you have MS, does having surgery or recovering from an infection cause any of your symptoms to get worse, at least temporarily? Do you get relapses, or do you find that you're having trouble with cog fog in a way that maybe you hadn't before? Because that would tie in with what they're saying here, which I think is pretty interesting. This priming of microglia could even be behind Alzheimer's disease. The main risk factor for Alzheimer's is age, and if microglia become more ready to respond as we get older, it could be a factor. At the same time, one of the main hallmarks of Alzheimer's is the buildup of clumps of amyloid protein in the brain. This process begins decades before symptoms of confusion and memory loss become detectable. One of microglia's jobs is to hunt down and remove these plaques. So it's possible that over time, repeated activation causes microglia to permanently switch into rogue mode. The accumulation in the brain of amyloid induced microglia to become more reactive, says Derrico. They start to release all these inflammatory signals, but the point is that since these amyloid plaques continue to be produced, there is constant, chronic inflammation that never stops. This is really toxic for neurons. Chronically activated microglia can engulf and kill neurons directly, release toxic reactive species that damage them, or start over-pruning synapses, destroying the connection between nerve cells. All these processes could ultimately lead to the confusion, loss of memory, and loss of cognitive function that characterizes the disease. And I'm thinking as I'm reading this that some of that sounds like what happens with MS too. In a 2021 study, Dorico even found that microglia can contribute to the spread of Alzheimer's disease by transporting the toxic amyloid plaques around the brain, just when you thought things couldn't get any worse. In the early stages of Alzheimer's, there are particular regions in the brain that seem to accumulate plaques, such as the cortex, the hippocampus, and the olfactory bulb, says Dorico. In the later stages of the disease, there are many more regions that are affected. We found that microglia are able to internalize the amyloid protein and then move to another region before releasing it again. Now, that I don't think has anything directly to do with MS, but just the fact that microglia can do that tells me that if they can pick up amyloid proteins, they could certainly pick up other things. So what it's sounding like is it's not that the microglia don't do their job, it's that they do it too well. They say that some of the symptoms of Alzheimer's, such as forgetfulness and loss of cognitive function, are similar to those suffering from long COVID, and it's possible that errant microglia could be behind brain fog too. For example, one of the main factors that cause microglia to turn rogue is the presence of a viral infection. Abnormally activated microglia may start over-pruning of synapses in the brain, and this may lead to cognitive decline, memory loss, and all those symptoms related to brain fog syndrome, says Claudio Alberto Cerfetti, a neurobiologist at the Federal Fluminense University in Rio de Janeiro, Brazil, who summarized the evidence for this theory in a recent review article. The hope is that this new way of thinking will eventually lead to new treatments. For example, clinical trials for new Alzheimer's drugs are currently underway that aim to boost microglia's capacity to destroy amyloid. Yeah, because you could turn this to good, right? If it does this, why don't we make it work for us? And then the however comes. However, as with all Alzheimer's drugs, such a strategy would work best in the early stages of the disease before significant neural death has occurred. Well, we've heard that story a lot when it comes to remyelination too, so we totally get that. For addiction, one idea is to swap the errant microglia that have gone wrong with the normal microglia that are present in the brains of non-drug takers. This concept, known as microglia replacement, involves grafting microglia into the specific brain regions by bone marrow transplantation. However, such an approach would prove difficult. After all, active microglia are necessary to fight off infections. In fact, they're vital for brain function. So yeah, similar to like when we have the stem cell replacement, while you are waiting for your new immune system to kick in, you are very prone to infection, and the doctors are very careful to keep infection away from you. And this would be the same thing. In theory, yes, it could work, but keep in mind that you don't want to disrupt microglia all over your brain. It would need to be localized, says Watkins. Micro-injecting microglia into specific brain areas would be very invasive, so I think we need to look for something that's safe for all kinds of treatment. And I appreciate that. As you know, I'm really big on having safety as a priority. What a fascinating and tantalizing theory they have put forth, and with a lot of experimental data that's kind of backing it up. It may mean that we need to be looking a lot more at the microglia in addition to looking at B cells and T cells. There may be some other aspects of our brain chemistry and the cells in our brain that are causing the problems that we know as multiple sclerosis. And then an interesting video that I found that I want to share with you. It's from a researcher at the University of Alabama in Birmingham. It's not specifically about MS, but I do think you could see MS in between the lines here, especially as he's going to be talking about the role of microglia, and I like how he explains it. You'll also notice that he mentions Linda Watkins, the same scientist who is mentioned in the BBC article that we just went through.
Hi, I'm Dr. Jared Younger. I'm director of the Neuroinflammation, Pain, and Fatigue Laboratory. Most of the work I do is on treatments for chronic pain, fatigue, and cognitive disorders. Things like fibromyalgia, myalgic encephalomyelitis, chronic fatigue syndrome, long COVID, Gulf War illness. And I take a lot of different approaches to combating these disorders. So I do pharmaceutical work, so looking for new drugs. I do botanical work, supplements, and also interventional treatments like vagus nerve stimulation or brain cooling. But there's one thing that ties together all of these different approaches, and that is the microglia. If you've been listening to my talks, you've heard me mention these before, but I wanted to talk about them a little more in depth in this video. I thought it was a good time. So I want to tell you what I'm trying to do when I talk about we need to modulate the microglia, and I want to give you the nomenclature that I use. So when you watch the future videos, when I talk about specifically how we're trying to do this, you'll know what I'm talking about. So let me tell you the story about why I'm even talking about microglia. Why do I think they're so important? So when I was a postdoc in, let's say around 2005 in Arizona, I was working on fibromyalgia. And a lot of us were trying to figure out what in the world is going on with fibromyalgia, this chronic pain thing. There doesn't seem to be anything wrong with the body, but they hurt all over. Now, by that time, about 2005, we pretty much figured out that the problem with fibromyalgia is in the central nervous system. It's not actually in the body where you feel the pain. It's actually in the spinal cord and or in the brain. So it's a central nervous system problem. The issue is we couldn't figure out what in the central nervous system was actually dysregulated. So we had some groups looking at serotonin, some groups were looking at dopamine, some were looking at glutamine or glutamate, most often glutamate, and then some groups were looking at opioid dysregulation, and I was one of the ones looking at opioid dysregulation. So we're all looking at these different neuronal types and different neurotransmitters, and there were interesting things for sure, but there was something missing. There was clearly a missing piece. What we were finding was not explaining what we were seeing, and the condition wasn't responding to the drugs that you would expect if these neurotransmitters were dysregulated. And so something was missing, and that's what was really bugging me kind of during this time. So I'm sitting at my desk one day, and a big fat paper just gets plopped down in front of me in the desk. And I looked up, and it was one of my mentors at the time, John Rich at Arizona State University. And he just said, you need to read this. So I picked up the paper, and it was called Glia as the Bad Guys. And it was written by Linda Watkins and Mark Hutchinson and their colleagues who I've mentioned before. And the short story was that this was the missing piece that I had been looking for. Now, finally, things started to make sense. And the major shift was we've been looking at neurons this whole time, but it wasn't the neurons that was the problem. It was the microglia. The neurons in our brain are just transmission lines. They're just sending messages. The microglia are what are in control of everything. So everywhere there's a neuron, there are microglia reaching out and touching the neurons and touching the synapses and controlling what the neurons do and what happens at the synapses. They can modulate the neurons. They can destroy a neuron if they want. They can prune back the synapses. They can change the way the neuron responds to neurotransmitters. And so all this attention we gave to neurons, while they're very important, like you have to have neurons to transmit messages, it's actually the microglia that are changing things. And so when there's a problem occurring, it is more likely to be due to the microglia adopting a pathological state. And so what I realized after reading this paper, and I'll put a link to it. It's probably open access by now. I'll put a link in the description in case you want to look at it. It's a long paper, but it's very, very interesting and a pivotal paper. And so what I realized is that we can't win against fibromyalgia by going after the neurons. We have to go after the microglia. And this is a very different approach than was conventional because all of the treatments were about neurotransmitters. They were looking at serotonin and norepinephrine, things like that. And what I realized is that's not going to work. If the microglia aren't in the right state, it doesn't matter what else we do. So we have to push the microglia out of the pathologic state and into the state that we want, that returns a normal state. So there's no more pain and fatigue and cognitive problems. So let me tell you what that means. Basically, the microglia, as I mentioned, they're cells and they're everywhere you find your neurons and they're controlling everything. Now, the interesting thing about the microglia is they can change states very rapidly, at least within a few minutes. And in some cases, I've seen evidence that they can change in a few seconds, but we'll say generally in a few minutes. So quite rapidly, they can change their shape very considerably. And when they change their state or their form, they have a different function, radically different functions. And so I'm going to draw while I talk and demonstrate what I am talking about. So there are 4 states of microglia that we're chiefly concerned with. There are other states, but there's only 4 that we're going to talk about now that are most important. So the first one is the resting or quiescent state. And there are other names for it, but I'm just going to call it resting. And this state is also called the M-naught state. And in the M-naught or the resting state, the microglia they're doing things. They're not truly resting, but they're not causing inflammation in your brain. And they're not actively combating inflammation or immune triggers. They're basically doing kind of a house cleaning functions and support functions. And this is where you want your microglia most of the time. They're looking for problems. They're surveilling the environment, but they're not making huge changes to the environment. And so when your microglia are in this state, you probably feel pretty normal. This would be the normal state for a healthy individual. So then there's the activated state. And the activated state is also called the M1 state. And when the microglia are in the activated state, they produce pro-inflammatory cytokines. And these cytokines cause your symptoms, whether it's fatigue or pain sensitivity or cognitive problems or malaise, dysphoria. It's being caused by these cytokines released by the microglia in the brain. So these microglia can move back and forth between resting and the M1 activated state. But there's another form of the microglia, which is anti-inflammatory or the alternative state. And we also shorthand call this the M2 state. Now in this state, it looks kind of similar to the M1, but it's doing a very different thing. Instead of pumping out pro-inflammatory cytokines, pro-inflammatory agents, it's pumping out anti-inflammatory agents. And so if your microglia are in the M2 state, they're going to be calming down inflammation in your brain, in your central nervous system. And the microglia can also move back and forth between resting state and the M2 state, as well as they can move between the M2 and the M1 state. So that's 3 big states. Now there's a 4th one, and that's the primed or hypersensitive state. The microglia, when they're in the prime state, are operating on a hair trigger. They're ready to activate with very little stimulus. And so they can move, they can be pushed from the prime state very readily, very easily. They can be pushed into the activated state. And so your microglia start to react to things in your environment, in your internal environment, that they normally wouldn't react to. So they're very, very sensitive. So you've got moving between primed and M1 very quickly. So what do we need to do? Well, obviously, I believe that if you have these conditions I mentioned, like chronic fatigue, like fibromyalgia, like long COVID, like Gulf War illness, your microglia too many of your microglia are in the prime state, or too many of them are in the activated state. And we have to change that if you're going to feel better. So we have to move the microglia back to the M-naught state, the resting state, or we need to push them to the M2 anti-inflammatory state. And every treatment that I try is designed to do that. I'm trying to return microglia to resting and keep them in that state so you feel normal and you feel healthy. And we do that by changing the microglia so we reduce the inflammatory agents that are being released in your brain. And that will calm down the pain, the fatigue, the cognitive disruption, and all the other things. So how do we do that? Well, that's a topic of other videos. There are many different targets on the microglia, direct and indirect, that could accomplish what we're trying to accomplish with them. There's also many different approaches. As I mentioned at the first of this video, there's pharmaceutical, there's botanical, there's interventional, there's also behavioral. So just learning what to avoid to keep from aggravating the microglia might be enough in some cases to get rid of a lot of these symptoms. So there are probably hundreds of possibilities. And as I've said before in previous videos, my job is to try to figure out what are the most promising approaches and then develop them and test them.
Let's not think we have to wait for the research in multiple sclerosis to catch up with the general field and start looking at microglia. Remember in our last video, we looked at an article that talked about the experimental research that's going on right now, and one of the projects they mentioned was one of the BTK inhibitors, remibrutinib. And as they say here, it's an oral treatment that potently and selectively inhibits the Prudence tyrosine kinase enzyme, which plays a critical role in the inflammatory activity of certain immune cells, such as B cells and microglia. So it looks like they're going to combat both types of MS progression. They're going to combat the first phase, which is the inflammation and visible lesions, and the second phase, where the microglia are center stage and taking over the main role in continuing the smoldering MS and the damage that we get from that. And so let's keep an eye on that, and I'm sure there's others too that are going to come down the pike looking at this in the same way. Unless you think I'm the only one paying attention to this, I went out to the clinicaltrials.gov website to see if there was any research going on in the intersection between microglia and multiple sclerosis. I looked for multiple sclerosis, microglia, and also microglial because I wanted to be sure that that turned up also. And I came up with 9 total studies, and I'm not going to go through these in any detail, but I will post the link below so that you can take a look at them. But as you can see, there's one here that's recruiting the effect of ocrelizumab on brain innate immune microglial cell activation in MS using PET scans and MRI. There's one here that's active and not recruiting, and I think that what that means is that they are not going to be adding any more people to this study, but the study is still ongoing, and it looks like it might be interesting. There's another one that's recruiting. This one's looking at ofatumumab. And here's another one that is active and not recruiting. They're looking at cladribine. And here's one that's looking at Mayzent, and that one's completed, but it doesn't show that results have been published yet. And here's another one that's active and not recruiting, so it's continuing on. They're looking at teriflunomide. And then finally, this one here is on imaging of intracerebral inflammation in multiple sclerosis, and that one is also completed, though there are no results posted yet. But it's just comforting to know that I am not the one who figured out there was this connection, because that would be kind of scary if I, a non-doctor, a non-medical professional, figured that out and none of the scientists in the world had. Well, all of this is really encouraging to me. I think they are really getting somewhere, understanding really the root of what's at MS. It's way beyond just the lesions that we see on MRIs. Could they have just jumped right straight into this? Did we really need to go through all these decades of variations on a theme with different DMTs? Well, I'm kind of thinking that they did. And part of the reason for that is because with multiple sclerosis, it takes so long for things to develop. In the early stages, most of us do have brain lesions, and those do seem to be like the problem that needs to be solved, just like when you go into the doctor with a broken leg. The presenting problem is your broken bone, not the fact that you perhaps needed to be doing more resistance training or more exercise in general because you let yourself get into such bad condition that your bones got brittle. We had an urgent problem to take care of, and we did take care of that first. The DMTs that are on the market now are demonstrably good at stopping relapses and keeping new lesions from forming and keeping the existing lesions from growing. But they don't take care of the smoldering MS that runs underneath it, probably from the very start. But this new line of thinking with the microglia as the culprits, again, what they're finding is that microglia that are good and helpful when they're functioning properly, for some reason with multiple sclerosis, they go rogue and they start doing things that they shouldn't be doing. And if they can be made to not do that, maybe, just maybe, MS will be a thing of the past. But that's all I have for you today. I'd love to hear your comments on it. But in the meantime, until my next video, please do take really good care of yourself, because things are happening thick and fast, and we want to be healthy so we can take advantage of them.